Yeah, I think the reading of the papers. So this is a review paper. You're not meant to do anything uh, yourself other than synthesize and really kind of deeply understand two or more papers. So it's really, the reading is the critical part. Reading and thinking and comparing is the critical part. Um, and I think everybody now has a solid set of papers that are that they're working from, and hopefully you'll find a few more as you go. But I think because this is a short paper, because you want a limited amount of time to discuss things, uh, you're going to want to select just a few ideas that are discussed in those two papers and maybe a few other papers to support your argument rather than trying to completely review all of the topics that are in the papers. So if you're feeling that like things are getting out of control, use a statement that says, that clarifies the scope of what your paper is on about. That may require changing the title of your paper, for example, or certainly changing the abstract or the introduction in order to keep things from getting out of hand. So that doesn't mean you can't think about a lot more things than you end up writing down. I'm just saying that one of the key pieces here will be being selective in what you choose to discuss. All right. Are there any other questions about that before we head on? Mingxi, could you mute your mic, please? Thank you. All right, great. So today we're going to talk about two papers of GHIs, as well a little bit a paper from Jason Wenegrat and Jorn Callies and Leif Thomas, and you'll see how that links up. So remember, we're continuing to think about the upper ocean boundary layer, which has turbulence in it, but also we're starting to think about where there might be a source of baroclinicity. And we have come to realize that there are at least two varieties of rotating stratified hydrodynamical instabilities, both frontal instabilities that would lead to small scale variations in the horizontal buoyancy. So whether the original gradient is caused by differential mixing or differential cooling, it's then strained together by the mesoscale eddies and then fronts sharpen through a process called frontogenesis, but then those fronts go unstable. So we expect on slightly, we don't know how big the horizontal gradients will be or what scale those will come from. So in this simulation, no horizontal gradients were put into the flow, and it's a 300 meter by 300 meter simulation. And so the Langmuir cells are here, and they're causing convergences and divergences, which, when we talked about Langmuir, we saw that oil patches would cluster along the convergence zones of this kind of turbulence. But we're trying to think about the next scale up. What are the slightly bigger features? And because we expect that what might make them dynamically different from just a collection of Langmuir cells is the fact that as we get bigger, we tend to get slower. As we get slower, we tend to feel the effects of rotation and stratification more. And so our overall class topic of rotating stratified turbulence is really coming into the forefront, where we think about how this boundary layer turbulence meets the larger scale turbulence and what that looks like. So the first paper of GHIs that we're going to discuss is the size of submesoscale baroclinic instability globally. And so that really is going to describe the size. And by baroclinic instability, we talked about this last week as mixed layer instability. But these are the big rotating eddies, relatively big rotating eddies that exist within the boundary layer. And so the key question is which boundary layer parameters predicts the size of these eddies. And so we've seen simulations with these eddies in it. We've seen them when they're together with the turbulence in the Hamilton paper that we discussed, and we've seen them when they're on their own in the paper mine from whatever 12 years ago. So those are the pieces that we're putting on, that we're trying to discuss now. Let me make this a little bit smaller. Okay. So the horizontal spatial scale is a baroclinic geostrophic branch, mixed layer instabilities. So that's the baroclinic geostrophic branch is one of the classes of hydrodynamic instabilities. It's the one that the Charney, Stern, Pavlovsky stability criteria apply to. It's not the symmetric instability that we talked about last time. This is the bigger one. And so those are the ones that led to mixed layer eddies. We can't really study the scale of the mixed layer eddies through thinking about an instability, because as we've seen a bunch of times, once the instabilities get started, then we get a cascade, like a turbulent cascade, and the scale spreads out somewhat. But we can talk about the original instability scale, the fastest growing scale, and so that's what we're going to try and do. So, and there's an interesting method here that GHI has used. So three high vertical resolution boundary layer schemes are driven with profiles taken from the MIT GCM global submesoscale permitting model. So there's a simulation of the whole world at 2 kilometers, which I think we discussed really early in the class. But anyway, this is a global high resolution. So it's submesoscale permitting. So it might have some of these geostrophic branch instabilities resolved, or it might not. We don't know until we figure out how big they're supposed to be. And then GHI takes a profile from that simulation, a vertical profile, and puts it into one of the boundary layer schemes, like the ones that we discussed in the Lee et al. Paper. So that paper had 11 different schemes. This one just has 3, but you'll see that the distinctions between the different schemes importantly shed uncertainty into how big we expect the MLI scale to be. So let's step this back again. All right, we take a profile from a model that might have MLI in it or might not. We put that into a 1D model, and there are 2 reasons why we would do that. One is because we can increase the vertical resolution down to where resolution is no longer an issue. The second one is because it'll allow the unresolved turbulence to take on a variety of different answers. So the boundary layer depth might get a little bit deeper, or might get a little bit shallower, depending on which mixing scheme we're putting it into. And so that uncertainty in the amount of turbulence is part of the uncertainty that gives us questions about the boundary layer scale. So the boundary layer scale is going to be the key parameter we need to find out how big these mixed layer instabilities are predicted to be. So the fastest growing MLI wavelength decreases toward the poles, which is a sign that Coriolis is important. The median surface MLI wavelength is 36 kilometers to 3.7 kilometers. So that's pretty small. That's very small. And quite a bit smaller, kind of 21 to 19 and 2.9 to 1.5 kilometers, using the parameterizations, the 3 different parameterizations. Remember, KPP is one of the ones we discussed. We discussed second moment closure, so that's what these other 2 are effectively. So we have a variety of different schemes to give us a different boundary layer conditions. Then there's some discussion about seasonality, and there's some discussion about the resolutions. We'll come back to that after we get a little bit more clear. Okay, so how do we figure out how big these eddies or these instabilities are going to be? Well, but this branch, the geostrophic branch of instability, tends to have the fastest growing mode governed by the deformation radius. So the deformation radius is just the stratification times a height scale over the Coriolis parameter. The stratification here is the stratification of the mixed layer. It's not the whole depth stratification because we're not trying to get the mesoscale instability scale. We're trying to get the submesoscale eddies, the ones that grow within the boundary layer. Similarly, the depth we're thinking about is the boundary layer depth. So those two parameters are the key parameters that are being extracted from the 1D mixing model in order to make a prediction of this deformation radius. To do this from observations, GHI is taking N and H as parameters that are coming from the Argo float profiles. So those observations allow you also to estimate these two parameters, which is probably a more realistic estimate because, as we know and have been discussing, the 1D schemes have a lot of diversity in them, and apparently there's a systematic error versus the observations. The observations tend to be larger in scale than all of the boundary layer schemes are predicting. They could be larger in scale because the depth is different between the different schemes and the observations. That's actually not so much the situation. It seems to be that the real observations are more stratified. But there's a combination of errors in both of those parameters that's leading to the different estimation of scales. Now, for the quasi-geostrophic ED problem, we're assuming that an ED instability, so that's the one with the constant stratification and shear across the boundary layer, that one is maybe the simplest case of baroclinic instability. That has a length scale that's approximately 4 times this deformation radius. So that's one key piece. It's not that the size of the eddies is equal to the deformation radius. It's some multiple, so it scales with this parameter, but it's a known scaling factor. But in quasi-geostrophy, the two assumptions that we make are small Rossby number and large Richardson number. Since this is the boundary layer, we don't actually expect quasi-geostrophic predictions to be terribly good. It's actually a relatively large Rossby number, relatively small Richardson number, maybe order 1 for both. And so we can actually, some theory was done by Peter Stone in the 60s that allows us to have a non-quasi-geostrophic prediction of that length scale, which has this extra factor of not 4R, but 4 times the square root of 1 plus 1 over the Richardson number. So if the Richardson number is something between 1/4 and 1, or a small number like that, this is a small correction, a relatively small correction, but it makes the length scale about a little bigger than 4. So GHI uses as a rough parameterization of this, he uses a factor of 6 here instead of the 4. So the instabilities tend to be a little smaller than the eddies will be because the eddies will have this cascade process, but not by much. So this is a pretty decent estimate of what the length scale that you would need to resolve if you wanted to resolve the instability itself. So if you were in a fully nonlinear model, if you had a grid scale that resolved this length scale, then you would expect those instabilities to occur in your model, and then the nonlinear part, turning them into eddies, having them grow a little bit, would also be resolved because they tend to get larger rather than getting smaller because of the inverse cascade typical of this kind of quasi-geostrophic or quasi-two-dimensional flows. Does that make sense to everybody? Okay, so we're gonna be estimating this deformation radius. We're gonna use the linear instability theory to give us a scale factor that's gonna give us the size of the eddies. So how do we estimate these parameters? So here is a typical profile of potential density, and then a typical profile of velocity in 2 different directions from a particular location in the Pacific Basin. So and then this is what this is down near the bottom, you see that there is actually some density stratification. So there's a boundary layer at the bottom and the top. This is low, so low density and relatively high but uniform density. Low uniform in the vertical density at the surface, high uniform in the vertical density at the bottom. Those are the two boundary layers we're thinking about. The other thing that we're getting out of the 1D model are these profiles of velocity, which are responding to both the initial conditions that are coming from the high resolution in the horizontal MIT GCM simulation, but also the winds are being forced and the amount of stress at the bottom. So this is a little bit fancier than just using the Monin-Albakov scaling to kind of get at what the shear profile and the depth of the mixed layer would be, but it's a similar idea that you're relating the boundary layer turbulence to the governing parameters of U star and W star, all those sort of things evaluated at surface, evaluated at the bottom, using that to get a profile of these, and then taking that profile, which gives you the shear and the depth of the boundary layer, and using that in that preceding formula to figure out how big the eddies are going to be. It's actually kind of difficult, as Anna really knows, to figure out how you figure out where the boundary layer is. Like, is it right here? Is it down here? Is it over here? You know, like, what defines the base of this boundary layer? And so if you take a look at the paper, there are kind of quite a few different methods that GHI experimented with, 5 different methods. And the way to pick a good one is to find one that robustly predicts the scales that the instability happens at. And so in this problem, if you do a linear instability calculation using a quasi-geostrophic model, you actually get 2 peaks of fastest growing modes. You get a mesoscale peak, you get a submesoscale peak, and you get ones that are intensified at the surface and ones that are at the bottom. And through identifying the rates of those different rates of growth, you can find the optimal choice, which is this R-var method, which seems that's the thick red line here, and that's the thick blue line here, which seems to do a pretty decent job of predicting the wave number and of the upper mixed layer instabilities, the surface mixed layer instabilities, and the bottom mixed layer instabilities. So now we have a method to determine what the depth scale is. We have a method, and then once we have that depth scale, we can evaluate the stratification on average but from the surface or the bottom up to that depth scale. That gives us all the parameters we need to find the deformation radius. Then the deformation radius gets used to find this length scale of the mixed layer from that, for the surface mixed layer instabilities and the bottom mixed layer instabilities. So, without more fiddling, here is the answer. This is what it looks like. So this is, as far as we can estimate from this approach, the surface mixed layer scale, surface mixed layer thickness. So here are the observations at the top. This is a wintertime and a summertime condition. So in the winter, this is winter in both hemispheres. Is it? I don't remember. Yes, I think it is winter in both hemispheres. And then this is summer in both hemispheres. So the depth of this surface mixed layer is deeper in winter. This goes up to 500 meters. This goes up to only 150 meters. So it's about 3 times deeper in winter than it is in summer. The Southern Ocean has really deep mixed layers year round. And these regions of the gyre, the subpolar regions, have deep mixed layers in wintertime. This top layer is from observations, and then these 3 below are from the 3 different boundary layer schemes, KPP, Miller-Yamada, and K epsilon. And you can see that actually, even though we we'll find that these observational estimates give you larger deformation radii than the boundary layer schemes do. The observational estimates are based on the observational estimates include other processes like the restratification that comes from the submesoscale, that these are all missing. So maybe it's not so crazy to think that the mixing schemes would be a little systematically deep, which they seem to be, and also that they might be a little systematically too well mixed, which they also seem to be. So that misestimation of the 1D scheme seems to be consistent with our understanding that the submesoscale restratifies while the 1D vertical mixing destratifies and deepens and entrains. Okay, so let's see, any other features to see? Oh, you can see that there's a pretty wide spread among these three different schemes. So we definitely should not, we don't know which one of them is right. None of them really matches with the observations. And that's true in both the depth scale and the buoyancy frequency. So instead, but these are the things that would be found in different models. So we're trying to anticipate how much scatter among different models might be a result of the 1D schemes versus how much scatter there is in the how distant they are from the observations. So all of that is part of what we're trying to assess with this kind of combined figure. So, and here then are the length scale, which is 4 times the deformation rate, or 6 times the deformation radius, derived from the observations in the top, wintertime, summertime, and the 3 1D schemes. And you can see that the observations are systematically a little bigger. So this is 50 kilometers horizontal scale at the top. They don't quite make it to 50 very often. In the summertime, they're smaller than in the wintertime. Summertime smaller, and that's consistent. But these boundary layer schemes are systematically smaller than the observations, but they have roughly the right distribution meridionally and some of the same features that you can see. You know, how the that there's a lot of latitudinal bands. It may be a little bit that this center of the gyre that seems to be deeper here in the Pacific is maybe not so obvious in the observations. That's interesting to think about, whether that is an indicator of strong submesoscale activity. But clearly the subpolar gyres in summer are much smaller scales. And that's true down here around Antarctica as well. In fact, down near Antarctica, it seems to be smaller scales year-round. But and so that means that the submesoscale is really quite small down there. Looking at it in zonal average, since these are relatively uniform zonally, we can take the zonal average. And so you can see now that the length scales range from about 2 kilometers up to about 30 kilometers, slightly larger scales in the northern hemisphere than the southern hemisphere. And the observations, though they are systematically deeper, the scatter around the observations and the scatter around the models tends to overlap. So choosing an individual location from here is not necessarily going to be larger or smaller than that same location in the others, but the average certainly, when you have removed some of the noise in this field by averaging, you can see that the averages do stand out quite a bit, to be different from each other. Similar in the median, I guess, rather than the average, since it's noisy and not Gaussian, is what we're showing in A, the winter, and B, the summer. You can see that the winter is a little bit deeper than is a little bit larger scales than the summer. So this is how big the submesoscale is based on this definition. One of the interesting things is, we're also getting a bottom boundary layer. And so you can do this same calculation, although we don't have good observations, because the Argo profilers don't go all the way down to the bottom, because they might get stuck in the biogenous ooze, as it's called, which is the kind of sticky dead things that have piled up covering most of the ocean seafloor. If you don't think of the ocean seafloor as being covered with sticky dead things, maybe that's a helpful thought. It is actually what most of the ocean seafloor is covered with. So, um, anyway, it's very kind of mucky in much of the world oceans. So if you were to send an Argo profiler down, it would have to be very smart to avoid getting stuck in the mud. So instead, they don't make them profile all the way to the bottom. They just profile down to either 1,000 or 2,000 meters and stay there and then come back up. So we don't have the equivalent observational data set of the deep ocean with global coverage that we do of the surface ocean. So that row is missing from the bottom boundary layer scales. But the other locations you can get by doing the same game, where you're taking the MIT GCM, projecting it into the 1D vertical mixing schemes. You really need to do that in the bottom boundary layer because the vertical resolution of the MIT GCM is very poor at the bottom. So using the 1D scheme allows for a sensible profile to be made out of the different forcing parameters down there, like Mononobakov scaling similarity would give us. And you see a few things are different. One, these numbers are a lot smaller than this number. So 5 times smaller, 10 times smaller for the K epsilon case. K epsilon is really predicting small length scales in the bottom boundary layer. And then the other important distinction is, look, the summertime and wintertime are almost the same image in the bottom mixed layer. So there's very low seasonality in the summer versus winter case of the bottom mixed layer and pretty strong seasonality of the surface mixed layer. The other piece that you can see here is, well, so how big are these scales? Well, here they are put on. I tried to match these axes kind of as best as I could. So here's 8 kilometers, here's 1 kilometer, here's 1 kilometer, here's 8 kilometers. You can see that the variation in the meridional direction is much weaker in the bottom mixed layer case. And also that the scatter among the different schemes is proportionally larger. The scatter here is almost a factor of 10 different between the deepest boundary layer scheme, which appears to be KPP, and the thinnest boundary layer scheme, which is the K epsilon. So we don't have observations in the bottom mixed layer. So this is a lot less certain than the surface case, but nonetheless, this is what it looks like. And let's see whether there's anything else I want to say about that. Oh, and this is the summertime, and this is the wintertime. Summertime, wintertime. So, wintertime, summertime. So you can see that there's no real distinction not only with latitude, but also with summertime versus wintertime here, whereas there's a pretty big distinction between summertime and wintertime in the surface mixed layer. So you might get worried that the bottom boundary layer is quite a bit different because it actually doesn't have a flat bottom everywhere. It has kind of sloping surfaces. And we talked a lot about features, roughness length variations affecting the Mononobakov scaling, but also, lee waves and all those kind of complicated things. The other paper that I pointed everyone to for today, this paper by Jacob Wenegrat, who's now at the University of Maryland, and Jorn Callies and Leif Thomas, tries to discuss that. So they're imagining a bottom boundary layer over a sloping surface. And when you do that, you actually get another dimensionless parameter to think about, which you could think of it as, what's the slope of this surface versus the, isopycnal slope or something else that you might want to compare to. It turns out that one of the most relevant ways to think of that is to think of it as the the slope Berger number, which is essentially, it's like a Berger number, except it's in that it's a deformation radius versus some other length scale, but it is based on a length scale that you're getting from the slope. It's sort of like, how far do you have to go horizontally to get to the equivalent scale of the deformation radius based on the boundary layer depth. So it's a combination of those parameters. the class of instability that they did a high resolution simulation of the bottom boundary layer, and they tended to find that most of the energy was coming from buoyancy production, which means that it's probably dynamically quite similar to the mixed layer, the geostrophic branch mixed layer instabilities. That remember, they are converting potential energy into kinetic energy. And so that's true of this bottom boundary layer scheme. But they also found at different slope Berger numbers evidence for other things like a convective instability. If you at small Richardson number, you can start to have Kelvin-Helmholtz overturning, or convective instabilities, or you can have symmetric instabilities like we talked about last time. So they have a different regime diagram here, which so in GHI's estimation, we always assumed that the slope was 0. So we were only down here on this axis, which either could have the balanced instability, the baroclinic instability, the one that we were just discussing, or maybe the symmetric instability over here, where the Richardson number is below 1, which is the same as the potential vorticity being negative. So down here is where we think about those two instability classes. But then up here, as the slope increases, we get a variety of other instabilities coming into play. So if you were sitting at a Richardson number of 2 and there was no slope, you'd say, oh, the only instability I have is the baroclinic instability, which is the one we just talked about. But if you go up here to where the slope Berger number is 1, then in fact that is not the fastest growing mode anymore, and instead you have a symmetric instability, or a kind of a hybrid symmetric convective instability that's the fastest growing mode. And if you went still higher, you would get to where the convective instability, something sort of like, am I saying convective and I should be saying centrifugal? I probably should be saying centrifugal, sorry. The centrifugal instability, which is related to the symmetric instability, but a little different in the way that the term balance comes out. So that's so over a sloping bottom, things are a little bit more complicated. But as I said, the abyssal ocean, the deep ocean, is actually covered with this biogenous ooze of dead things, which makes it incredibly flat. So you may, if you've been somewhere like Kansas or the prairies of Colorado, you know that it's extremely flat, much flatter than the joke is that it's as flat as a pancake. It's actually much flatter than a pancake. The surface of the Earth, when sediment is allowed to accumulate under modest stirring, very closely matches a geopotential surface. So when these kind of silty sediments from plankton settle down on the bottom of the ocean and then get gently stirred by these currents and boundary layer flows that we've been talking about for the bottom boundary layer, it tends to really eliminate any little hills or bumps. And so the abyssal ocean is extremely flat. It's much flatter than the continental surface, which has lots of other processes and does have erosion working on it. But erosion is not as effective at flattening the landscape as filling things up with sediments from dead things, primarily. Okay, dead phytoplankton and dead zooplankton. Okay. Yeah, so, all right, that's an interesting thing to think about. But so, while it is true in some of the places where the bottom boundary layer mixing is most intense, we know from observations of bottom boundary layer turbulence is over rough topography. These higher slope Berger numbers are really what we'd expect where this turbulence might be most intense. So there are places in the world where the slope is really important, and then you might expect to get up into a different regime of instability, but away from those places is where this estimate that GHI has produced tends to be a good one. So in those rough topography regions, you might expect the scales to be somewhat larger, and also to expect that the classes of instability might be a little bit more towards the unbalanced ageostrophic scales. So how well then does this MIT GCM do in resolving the surface mixed layer and bottom mixed layer eddies? This is an estimate from of the resolution of high resolution ocean models coming down this axis, and these are all very high resolution ones that were used for the IPCC reports in previous reports, going back to the first assessment report back here, and now this is the 6th assessment report model, highest resolution. This is the MIT GCM that GHI took the profiles from. So it's significantly higher resolution by an order of magnitude than the high resolution models in the IPCC. So it kind of jumps off of this dashed line, which is the expected rate of computer increase. But of course, these are climate models run for centuries, and they have atmosphere and other things. This is an ocean-only model run for only 2 years. So you would expect it to jump off. But does it jump off enough and get to fine enough ocean model resolution that it's resolving all these submesoscale features? Well, qualitatively, it definitely has submesoscale features in it. You probably have seen movies from this, these kind of simulations. Well, I have shown you movies even in this class of this kind of simulation at this 2-kilometer resolution. And it does have submesoscale features in it. There are mixed layer eddies in this simulation. But this dark band shows the resolution you need to get the median, so 50% of the grid points or 90% of the grid points, to resolve the surface mixed layer eddies. And you can see that it's about a factor of, I don't know, it's maybe a little bit more, a little less than less than a factor of 2 finer resolution. So if you went to 1 kilometer resolution rather than 2 kilometer resolution, you would be able to get at 50% of the grid points, you'd be able to get that length scale resolved. But you wouldn't get to 90 until you get down to about 800 meters or so, 700 meters. The summertime submesoscale mixed layer eddies are even smaller. So there, the 50% is down near where the 90% is for the wintertime, and the 90% is about an order of magnitude finer resolution than what we can presently afford. So if you're making an estimate of seasonality, like whether the submesoscale is stronger or weaker in summertime, you actually need this dot to be down here about an order of magnitude finer than we can presently do. The bottom mixed layer is even harder to resolve. So this pink and this green are doing the equivalent of what the dark blue and the light blue did for the bottom boundary layer. And the K epsilon one is down here, which is, remember, this is the one that really was fine. And so we have a much wider range of uncertainty in the bottom mixed layer. We don't really know we have no observations to compare for here, so we don't know. But in the different estimates of the 1D scheme, it's somewhere between an order of magnitude and 2 orders of magnitude greater resolution that would be required to get this dot down here. So we are comfortably resolving all of the submesoscales in the surface and bottom mixed layer. So that's for the baroclinic instability. Are there any questions here? I want to close on contrasting to the symmetric instability case. Okay, great. So GHI has taken this same approach and used it to estimate the size of symmetric instability globally, and also the activity of the symmetric instability. But we're just going to talk about the size here because it's an important comparison. Oh, sorry, this is the wrong abstract. This is the abstract from the other one. But this paper is still in preparation, but it'll probably get submitted soon. But it basically takes the same approach and finds quite a bit smaller eddies. So why are they smaller? Well, here's that scale that we were talking about. This is the size of the eddies for the baroclinic branch. And here's the equivalent formula for the symmetric instability branch. So it still depends on the Richardson number. And as the Richardson number approaches 1, this length scale gets smaller. So if we find from the output of those models that the Richardson number is approaching 1, this is actually getting smaller. So it is a bigger instability the more well mixed the boundary layer is, but a smaller instability as you approach that. And that's because Richardson number 1 is actually the cutoff, the symmetric instability cutoff, at least for a flat surface. This scale out here, U over F, is not the deformation radius. It's because it depends on the magnitude of the velocity. And so for something like an Ekman boundary layer, this might have a different scale than the deformation radius does. So that's another piece of the conversation that we might have. But suffice it to say, there are 2 different scale estimates, and we have all the ingredients to calculate both of these. From that approach of calculating the 1D schemes, calculating the stratification, finding the boundary layer depth, going ahead, calculating the deformation radius from the boundary layer depth, taking the profile of shear from those models, plugging it into here. So all the pieces to estimate these 2 scales are there. And just remember, we talked about the symmetric instability as being the one that occurs when the PV goes negative. That is when the density surfaces are very steeply sloped compared to the absolute momentum surfaces. That's equivalent to this balanced Richardson number being less than 1. So we're really only interested in this parameter when this balanced Richardson number is smaller than 1. So the first thing you might ask is, does that ever occur? Or is the Richardson number greater than 1 all around the world? Well, it actually occurs pretty often. One way to show that is to show that the potential vorticity is negative. So here is the monthly averaged PV, and you can see that it's negative. It's blue in the winter hemisphere, and it's red in the summer hemisphere. So the model, at least, is predicting that you should have symmetric instability all the time in the wintertime hemisphere. It's a little bit of that may be a stretch, because if we did have symmetric instability, the first thing it would do is eliminate the negative potential vorticity by mixing with the deeper positive potential vorticity, the way that we talked about the boundary layer, the Bachmann scheme working. But this at least shows that in wintertime there's the potential for symmetric instability. And then this is the likelihood based on surface conditions of how often that potential vorticity is negative, time step by time step, rather than in monthly averages. And you can see that it's a pretty big number, 80% of the time or so, 70-80% of the time in the wintertime hemisphere. So the forcing, as far as the MIT GCM at 2 kilometers resolution is concerned, predicts that there should be the potential for symmetric instabilities often. How big are they going to be? Well, the depth scale that we need to define now is not just, there are 2 of them. There's the one that is the big H depth scale, the depth at which the symmetric instability reaches to, that deeper depth where the potential vorticity is uniform. And then there's the shallower depth, which is where the potential temperature is going to be uniform. So this is a spatial distribution of the estimates of both the big H, the little h, and then the difference between them. And if there is no difference between them, that actually means that there should be no symmetric instabilities. So this is another way of calculating whether symmetric instabilities are active. And you can see in the wintertime hemisphere, you are getting basically the same places where the potential vorticity was negative. You get big regions where those 2 boundary layer depths are different. And that difference is about a few. So here's the ratio down here. So it's kind of in the 10 to 20% range, or well, I guess maybe 5% to 15% range in the wintertime hemisphere. So the symmetric instability will dominate in about 20% of this deeper boundary layer, and the convective boundary layer that's within the symmetric instability boundary layer will be in the upper 80% of that big H boundary layer. Okay, so the last question then is, how big are these SI going to be? if you crunch these two formulas for the boundary layers and for the surface symmetric instability, the symmetric instability are roughly 10 times smaller than the mixed layer instability. So somewhat similar pattern in that it's concentrated near the equator, smaller away. But these numbers are 2 kilometers would be the biggest symmetric instability. 10 meters would be on the small scale of these instabilities. And you can see that, so in the summertime hemisphere, the symmetric instability really, really is tiny. And so I think that's all I wanted to say. Basically, these global models that can permit the submesoscale are a long way away from being able to resolve the submesoscale, and a very long way from being able to resolve the 3D turbulence that's now parameterized with these different parameterization schemes that we talked about here. On the other hand, if we switch to the large eddy simulations, like we were talking about last week, the Hamilton one, we can resolve all of these phenomena, but only in a domain that's maybe 10 kilometers by 10 kilometers or 20 kilometers by 20 kilometers on a side. So we can get at all of the scales of motion to try and understand what's going on, but we have to build these parameterizations or estimates of scales, estimates of impacts, in order to figure out what they do to the globe as a whole. So we'll be in that situation of needing parameterizations and improving and developing parameterizations for a few hundred years, if you figure out how long it will take us following this Moore's law to resolve not only these smallest eddies that are of the submesoscale, but the still smaller eddies that are those of boundary layer turbulence. So we're talking about 2200 before we get in the ballpark of where we'll have a global ocean direct numerical simulation. Okay. Are there any questions? Are there any lingering questions about the homework?
Yes, I have a question about the homework. Just for a moment, I don't remember exactly the number. Sorry. Okay, it was number 5.
Okay. Let me pull this up. Okay, number 5.
Yeah, so okay, so the first thing is that in 19 equation, the parameters inside the brackets are two of them are repeated the same.
Yes, that's not very helpful, is it? Sorry, one of them should have been ZT rather than Z0.
Okay, so we are not supposing that Z0 is equal to ZT.
Frequently that gets assumed, but we don't have to from the perspective of just the Buckingham pi.
Okay.
Let me see if I can fix that right now.
Yeah.
Was that the question?
Yeah, and then I was thinking about the 8-dimensional parameters, and they are the one that are expressed in the first sentence. Is it this part?
Yes. 1, 2, 3, 4, 5, 6, 7, 8. Yeah.
Oh yeah, okay, because we are not supposing that Z0 and ZT is the same.
Yes, exactly.
Yeah, okay. Okay.
And frequently what does get assumed is that they are the same in parameterizations of this, and then you can write you can take, and also this assumption about the fact that the reference temperature and the reference turbulent flux scales like this, which eliminates still another parameter. If you eliminate both of those parameters, then you have something that has the same parameters plus T star as the momentum mixing scheme, and so a lot of climate models would use those two together. And so then you have just to specify what the roughness length is and the Monod-Nabokov depth you find from the background profiles and the surface fluxes, and then you know the profile of both the heat flux and the momentum flux through the boundary layer.
Yeah, but so in the first sentence, when we have both Q0 and Qref, but we also have, if Qref is equal to theta ref, U ref, is it not an abundance of parameters?
Yes. So there's more. So if you do not assume this is the case, then you could have a ratio of whatever this was actually equal to whatever this is actually equal to. So there would be one more parameter, and the ratio is sometimes called a Nusselt number, which is essentially if you had a diffusion and then a turbulent flux, the diffusion would govern these parts of the profiles or would be related to these, and the turbulent flux would be whatever it is, and that number might be greater than 1 or less than 1. So there is the possibility that I guess physically what you're saying is it's possible that the boundary layer turbulence is either more efficient or less efficient at moving heat than it is at moving momentum. So it is possible that the transport of heat, the Prandtl number, the transport of heat versus the transport of momentum is not equal to 1. And that would come into this. So that's another dimensionless parameter that you could think about. And in boundary layer LES, you might actually study what sets that relative efficiency. In a first pass, it's easier just to assume that those things are equal to each other. So I guess that's where I would suggest to think about it.
Okay, yeah. Still I think, okay, maybe I can say it differently. So if we have 8-dimensional parameters and 3 units, so we expect
5 groups. So here's 1, 2, 3, 4.
And 4, yeah.
And where's the other one?
I think it's because when we are writing Q0 over theta ref, U ref, we are not writing Q ref in these equations. So we are just assuming that Q ref is equal to theta ref and U ref.
Yes, exactly. The other one would be Q0 over Q ref, if you like. So
yeah, and so you have theta ref and U ref in the other.
And so making this assumption is actually reducing us from 8 because we're essentially eliminating Q ref. And then if we have 7, then we would expect 4, and here they are: 1, 2, 3, 4.
Yeah. Okay. Thank you.
Yes. Any other questions on the homework while I have it up? On Monday, and I will get through all the homeworks over the weekend. So we will have you'll have all of your pieces in place except for the final paper. And please do, if you have any questions about specifics or general about the final projects, please bring them. We'll start with that on Monday, and then we'll do a summary, which will kind of revisit a lot of the themes that we talked about in the first class, but now we can build them on things that you've seen in the class. So we should be able to bring all those pieces together much more meaningfully. All right. Thanks, everyone. Have a good weekend.
Thank you.
See you on Monday.